Hi, Larry.
Hi, Lil. How you doing?
I'm doing well.
Good.
Good. I will start the recording once people join. But
Okay.
did you wanna, you're good with Zoom? You know how to share a screen and do all of that and
Yeah, I think so. Let's see. Let me just make sure. Yeah, there's the green button for share screen. And then let's see. I'll start the. So we start in 12 minutes, I guess.
yeah, 12 minutes. And it looks like Natalie just joined us. Thank you,
Do you want
Natalie.
to?
Yes, hello. Yeah, I made go ahead. I went ahead and made you the host. So you
I
have
see
full
that.
control.
All these controls just popped up. So yeah,
Yes. Okay.
perfect. Thank you, Natalie.
You're
You're welcome
welcome.
to drop off and I'm all good now. So thank
Yep,
you.
that's what I'm gonna do. All right, thank you.
Hi,
Sorry.
Natalie. This is Larry.
She-
Hi, Larry, and bye, Larry.
Bye.
Okay. Bye.
Oh, there's Joelle.
Oh,
So Larry, the way it will work is I've got host privileges now. I think we're already recording. We
yes.
can clean
I
up
saw.
later, which is fine.
Morning,
Hi, Joelle.
morning, Larry.
Hey, Joel. How you doing?
Good.
So Joelle, you could maybe give Larry sort of a rundown. When you did this, Kurosh was managing the Q&A portion of it. So people can submit questions and I was gonna try to just, manage the questions and just say, hey, and if there's, I think, well, actually Kurosh could answer a bunch because he knew the technical stuff, but I will try to consolidate the questions into sort of a few questions so that when you have time, Larry, at the end, I'll have a list of questions that we can start with, basically.
Okay.
Yeah.
Okay. Do you
And
want
they
me to
can
share?
all unmute themselves, right? All the audience, they will be able to unmute themselves.
Yeah.
Are we already on the site where they will join?
Yes.
Oh, I see. Okay. Yeah.
So we've had a couple people pop in and then drop off for some reason. This happens a lot. So we'll see how many people actually come. But
Hey, Lily, do you want me to share my screen now?
sure, you can practice doing that.
Okay, let me just do that. Let's see.
Perfect. All good.
Right. Do you want me to just keep this up?
Sure.
Okay. And let's see. Make sure it's. I can change screens here. We could. So Joel, I'm using the Mossy Rock Dam picture.
Mossy Rock. I've never heard about it. Mossy Rock Dam. It's in Washington, huh?
It is. And the
Huh.
unusual thing about it, it's an arch dam, but it has this gigantic spillway and these huge piers
Huh.
on the upstream side.
Hmm.
So that's interesting. We need to figure out how that's going to impact the seismic response of that dam. And they have the big piers so that when the water flows out of the spillway, it doesn't go to the side and impact the power plant here.
Hmm. Usually the spillway, they are on the side, right? On the side of the dam.
Yeah, normally, and that's the best place on an arch dam because when you put the spillway in the center of the arch, you're removing arching action in the spillway area. You don't
Hmm.
arching goes horizontally, the loads go horizontal, so you have this disruption. So it's not the best.
Hmm. So you will talk about it during the talk, huh, as well?
No, I just have this as a picture. I'll talk
Oh, I
about
see. Okay, sure.
as other ones, but yeah, I know you're going to use this on the advertisement, but then you didn't have the rights to it. I'm not sure if I do either. A lot of this stuff you just get off the internet.
Yeah, I think Lely, I think Katie, she's extremely careful. I would not mind to take any picture I find on the internet to put, on the title page of a presentation.
Yeah, but you're definitely right. If you're publishing a book or
Oh yeah, then you cannot do that.
yeah, definitely.
Well, I'm recording some videos because I'm creating an online course for structural engineering for high school students. So it's fully
Oh.
online. And people working with me to create the videos and the PowerPoints are very strict about using, that's how I got access to some, they're very strict about using free open source images, basically, for copyright issues. So I normally pull things off the internet all the time because I feel like it's for education. It's not
Yeah.
not like I'm using it for anything, but yeah, they've been particular.
I agree. I tell you, I've had a wonderful career in the dams industry.
Yeah, it looks like you are passionate about it. That's why
It's been pretty fun.
Oh, I see, Larry, I don't know if you can take it down and fix the title page, but it says NARI, UC San Diego, and it says L post, but there's an H after the L, LH post.
Oh, okay. Yes, I will. Let's see. Let me get. See what happens if I.
And Lily, if you want to say anything, then I will introduce him. And then
Okay.
if you want to add anything, please feel free. Also, Kurosh.
Yeah, I mean, I think you can introduce him. That's great. I think the only thing is like, to say that this is part of a, quarterly webinar series kind of a thing that they should keep looking for exciting, other things coming down the pipeline, I guess. But you're welcome to say that too.
Yeah, Lillian, in 2008, I was just days of getting funding to do a large scale arch dam test on your shake table.
Really?
Yeah, and the funding was through FEMA, and they were gonna announce it on Friday, and the financial crisis hit.
Oh no.
And they lost all their funding, all their funding.
Ah, that's a bummer. I do remember that we were going to do something back then about dams. So yeah, it's too bad.
Oh, I know it.
I'm getting more people registering right now. So
Morning, Kurosh.
Good morning. Good morning, Larry. Good morning, Lily.
hi.
Morning,
Hi.
Crush. How you doing?
Doing well. How are you?
Good. So we got about 18 inches to 20 inches of snow yesterday and the day before.
Oh,
I
nice.
heard what is it like right now? Because I have friends that are like traveling through Denver and are worried they're going to be delayed. Is the airport okay?
It is. In fact, the amazing thing is here, I live on the west side of town, and we got, almost 2 feet of snow, and the airport got very little.
Wow.
Yeah, and they're just like 30 miles away.
That's crazy.
Yeah. And the roads are good too. So, but yesterday and the day before, Interstate 70 was shut down and it was a mess.
Wow.
But it's bright and sunny today.
That's great. So why don't we wait a few minutes as people are joining and then.
Do we see them? Do we see the audience, Lily?
I think in this format we do, right, Kurosh? I see people
Yeah.
joining. Do you not see people joining, Joel?
Yeah, I can see very few, right?
Yes,
So maybe we
4:30.
should wait. You think we should wait 5 minutes after or?
Probably a few minutes for
Yeah,
sure.
yeah.
I'll be here. I'm just gonna stay muted. If you need anything, let me know.
Sounds good.
Lily, do you want my camera on or off during the presentation?
I think you should keep it on.
Okay. You had a lot of flooding in San Diego this summer, huh? Or fall?
Yeah, we had a lot of rain the last couple months.
Larry, we wait a few minutes and
Okay.
so that more people will have joined, and you still have the same amount of time.
Okay, great.
Yes, good morning, everyone. We are still waiting a few minutes to introduce the webinar so that maybe a few more people will have joined by then.
It's pretty exciting. You now have 6 degrees of freedom on the shake table.
Yeah, you need to come and visit.
Yeah.
Yeah, definitely.
Okay, so I think maybe we can start. So good morning or good afternoon or good evening, depending on where you are, everyone. My name is Joel Conte. I'm a professor of structural engineering at the University of California, San Diego, and PI for the NERI experimental facility that we have here, which is a large shaking table called LH Post, like you see on the title here. that has been upgraded in recent years to from 1 to 6 degrees of freedom. And we have, as part of our NERI experimental facility, we have introduced a UCSD NERI webinar series. And I'm very excited to introduce today's speaker, who is Larry Nass. He is Larry worked for 36 years at the Bureau of Reclamation, where he has become a world expert in the design, the analysis, modeling of concrete dam safety, risk analysis, security of concrete dams. He is well known all over the world. He retired from the Bureau of Reclamation in 2011. He since then formed Nass Engineering, a limited liability company, from which he acts as a consultant on review board members on dam projects all over the world. He has taught classes in the United States. He got his Master of Science degree from the University of Colorado at Boulder in 1978. You will see he is so knowledgeable about the topic, and this is great because as part of this webinar, we try to attract speakers who can address very challenging research questions remaining in earthquake engineering, and so you will have a great webinar. So Larry, thank you very much for accepting to be a speaker in our webinar series, and the floor is yours. Maybe a few details about the question. If you have questions, please write them down, and then we'll manage them at the end of the webinar. And there is also 2 members of the UCSD NERI team here, Dr. Lely van den Einde, also professor in the Department of Structural Engineering, and Dr. Kurosh Lotfizadeh, who is our site operation manager. So we'll manage the question, but you can also unmute yourself at the end if you want to ask your question verbally. So if I'm missing anything, Lely and Kurosh, let me know, jump in.
Yeah, I mean, just when you say write down the questions, what you mean is there's a Q&A button down at the bottom of your controls on Zoom. So you're able to submit questions, and we'll manage them and try to help Larry organize the questions. And in the end, we'll try to get to your questions. But you're welcome to, like Joelle said, unmute at the end and ask your questions on your own as well. So
Great.
Larry, it's all yours.
Yeah.
Okay. Well, thank you very much, Joelle, and everybody. Good morning. And yeah, so this webinar, I'd like to present to you different concrete dam concepts and what's been developed over the years, and then the need for large-scale shake testing. So we'll jump right into it. And you may not know this, but in the United States, there's over 84,000 dams in the United States. There's about 700 federal dams and almost 45,000 private dams. And the issue with seismic analysis of dams is the downstream consequences could be enormous from the failure of a concrete dam. And I'll show some failures that have occurred early in the last century. But concrete dams have failed, but not from an earthquake shaking. They failed from flooding, from overtopping, from landslides, and it's mainly due to failures in the foundation. But so we have not experienced a seismic failure of a concrete dam. There's Shikang Dam in Taiwan was damaged pretty bad. I'll show you a picture of that. But from just purely seismic shaking, a concrete dam has not failed. So we don't know exactly. We've analyzed and we've done computer modeling of concrete dams, and we're basing a lot of our assumptions on analysis. But it's, the reason why we'd like to do a large scale test is to actually physically see a concrete dam fail. We've done small, like 3-foot high models, which I'll show some videos of that, but nothing of any size. So we'd like to see what earthquake magnitude they might fail at, and the duration. Some of the subduction zone earthquakes are quite long. So there's gravity dams come in all different shapes and sizes, but there's 3 basic types. There's a gravity dam, arch dams, and buttress dams. And I'll show you those. So here's at the Bureau of Reclamation. Reclamation has 385 dams in the Western United States. About 90 of those are concrete dams. And Reclamation is noted for having some of the largest in the world. A Hoover Dam was built by the Bureau of Reclamation in the 1930s. It's 726 feet tall, so it's almost the height of a 72-story building. You can see it's massive, and if you've ever been out there, it's worth the trip to go see Hoover Dam. Then there's Glen Canyon upstream from Hoover. It's 710 feet high. And you see, and then here's Mara Point Dam in Colorado, quite thin and narrow. And then look at East Canyon Dam down here, pencil thin, and it's 260 feet high. So why are some dams very thick and some dams are very narrow? So we'll show you why. The main reason is the type. And so a lot of it depends on the curvature of the dam. So here you can see, here's Hoover Dam right in the middle. It's curved, and so it develops a lot of its stability from just the curvature. It's like an eggshell. And then here's Friant Dam in near Fresno, California. It's a straight dam across the canyon. So gravity dams, they can be straight across the canyon. And they're held there by their sheer weight. They're big, they're massive, they're heavy, they're wide, and just the weight of the structure holds it, makes it stable. And so you have, you can basically think of the reservoir load as a triangle trying to push the dam downstream, and the weight of the dam, the concrete, is holding it in place. And so the forces from the reservoir are sliding it along the base and pushing it downstream. One thing about a gravity dam, they can be straight across the canyon, and they can be very, very wide. Here's some pictures of a couple of gravity dams. Here's Grand Coulee Dam in Washington. It's almost a mile long. And you can see it's stable. It's not getting any help from the abutments. It's so long, and it's just being held there by its weight. Here's a Canyon Ferry Dam in Montana. It's a gravity dam. It's straight across the canyon, and it's also held there by its weight. It's in a narrow canyon, so it does develop some 3-dimensional beam action, but basically it's stable because of its weight. Then there's buttress dams. There was a period of time when materials were hard to get. Concrete or cement was hard to get. Maybe the aggregates for concrete. So what designers did, they narrowed out, or they hollowed out a gravity dam, and then to make it stable, they're taking away a lot of weight. So then the upstream face of the dam is sloped underneath the water. So you have all this weight of the water above the upstream face. That adds to the weight that's missing here where they've taken it out. And so buttress dams are stable because of their shape and their design. And they're very efficient because they're hollowed out. One thing about buttress dams, you have to have reinforcement. So these are reinforced. Gravity dams are not reinforced, and arch dams are not reinforced. So here's an example of some buttress dams. Here's a Stony Gorge Dam in California. You can see the buttresses, and then there's always the upstream face. That in this case, it's a slab, a reinforced slab that's the water barrier. Here's Bartlett Dam in Arizona, and you can see its water barrier has these thin, or these arches. These arches take the load, the water load, and send the load sideways into these buttresses, and then these buttresses hold the dam in place. And here's a buttress dam, Coolidge Dam in Arizona, and it has these three big domes, and that's the upstream water barrier. And then these domes carry the water load sideways into these buttresses. So there's different shapes. There's a lot of different shapes and designs. There's no one standard concrete dam. Then arch dams are thin, they're elegant, and they carry the load very efficiently, and all the load goes horizontally. So it's like an eggshell. If you ever taken an egg and put it in your hand and then squeeze it, take your ring off. You don't want to have a concentrated load or anything like that. And just have your hand and squeeze an egg, and it is almost impossible to break the egg just by squeezing it with your hand. And that's because shells are so efficient. Arch dams have to be in narrow canyons, and they have to have very strong rock abutments so that the load can be transferred horizontally into the abutment. So you can see here's three arch dams. Here's East Canyon Dam, a very thin dam. This dam is 260 feet high, and the top of the dam is only like 7 feet wide. Here's Flaming Gorge in Wyoming. You can see the curvature, the shell structure. And then here's Glen Canyon. It's 610 or 710 feet high. So you can see they're all in fairly narrow canyons, which is a requirement. Here's to just show you how thin an arch dam can be, because all the load is going horizontally into the abutments. Here's Viant Dam in Italy. It's 858 feet high, and to show you how strong they are, this dam survived overtopping by 350 foot of water that was caused by a landslide upstream. So incredibly strong. To show you, look, this is a section view, a side view of the dam. Look how thin and narrow. It's incredibly narrow. There's no way that could stand up by itself. If it was a gravity dam, it'd just fall over. But because it's an arch and all the loads are going horizontally, you can make it very thin. So arch dams are popular because they don't take a lot of material, and it's mainly the shaping that's kind of fun to do, actually, to design one. Here's a Morrow Point Dam in Montrose, Colorado. This was the first what they call thin arch dam in the United States. It's 468 foot high, so that's like a 47 story building. And see how thin it is? It's just unbelievably thin. The crest is only 12 foot wide. But again, it's stable because it's carrying the load horizontally. And then there's a kind of a hybrid, a curved gravity dam. So we talked about how gravity dams are held there just by their weight, and you can build them straight across any canyon. They can be very, very long. And but to add extra strength, sometimes they take a gravity dam shape that's heavy, and they curve it. So here's Hungry Horse Dam, and by curving it produces a lot more strength. It's stronger during earthquakes, during floods, and so they're probably some of the stronger concrete dams. Here's Hoover Dam. So this is interesting. So look how massive Hoover Dam is. So it's definitely stable just by itself. It doesn't need arching action. But look how much curvature they put into the dam. And when Hoover Dam was designed and built in the 30s and in the 40s, there was some controversy whether a concrete dam could carry a reservoir load this big. And so they made it like a gravity dam, and then they curved it to add extra strength to it. Hoover's interesting. We reanalyzed that in the 1980s, and so the peak ground acceleration at the base of Hoover, the mean slope fault is only about a half a mile away, and it generates about 0.6, 0.7 G at the base. And because this is so tall, the accelerations at the top of the dam are almost 3 G. So that means that if earthquake would hit you, that at 3 G, you're being pushed sideways at 3 times your weight. And the interesting thing is that so these little towers here on top of the dam are decorative, but they're also the men's and women's restroom on top of the dam for the tourists that come to the site. So I said, well, if an earthquake hits at Hoover, you better not be up in those towers because there's going to be a lot of shaking up in the towers. So as concrete dams evolved, basically all concrete dams were gravity dams, heavy like this, and then they started making them thinner and curving them. And when you have a cantilever like this, you expect the dam to curve and to develop these red areas are tensions. So you expect the tensions, just like in a cantilever, to bend over, but you don't expect the tensions on the downstream side of the dam. And they were getting cracking on the downstream side. And basically what was happening was the arches, when they curve the dam, then you're carrying part of the load by the curvature and the arches in the dam. And so they were actually holding the top of the dam from deflecting, and they developed vertical tensions on the downstream face of the dam. So then what they did then is you shape, there's no reinforcement in an arch dam, so you shape the dam so that you create a counter moment, an upstream moment by the center of gravity here on this the bottom part of the dam, and so you get rid of the tensions at the upstream edge of the dam, and then you curve the dam downstream, so you develop this weight on the downstream side, and then you develop a moment going downstream, and you get rid of those tensions on the downstream side. So it's quite an art to shape an arch dam, and what you're trying to do is get rid of the tensions, because you want the geometry to carry the load and get rid of the tensions. You don't want to have to put in reinforcement in the dam, because they're so big and massive, it takes way too much reinforcement to put in, make it stable. So how are concrete dams built? Well, basically, all concrete dams are built on rock foundations. They excavate down through the soil and whatever and get to good sound rock, and then they clean it. So these guys are an old picture, but they're using high pressure water to really clean off the foundation. And see right here how clean that is. They want all these little pieces and the surface of the rock to be pristine, so that when they place the concrete on it, you get good bond between the concrete and the rock. And then in the early 1900s, so they would build concrete dams out of big rocks, and cement was hard to get, and concrete. So they would put these big rocks in the middle of the concrete dam, and then just push cement in between all the rocks. So those are called cyclopean masonry, and that's the way older dams are built. And then as things evolved, they started using mass concrete in concrete dams. So they put big aggregate or big rocks in the concrete mix. And if you ever seen the sidewalk out in front of your house being placed, the aggregates in that are quite small, maybe ½ inch or an inch. Here we have 6-inch to 9-inch diameter aggregate in these big dams. And then you can't place the dam all at once. So what they do, they built it in 50-foot by 50-foot blocks that are 5 foot high, and that's just enough to be able to place within an eight-hour shift. And so they form up a 5-foot high block and then place concrete. And as you know, concrete, when it hydrates, it develops heat. So when you build them in these blocks, you're separated by gaps in those between these things called monoliths. So you build them in monoliths, and that helps that concrete cool and not crack as it's cooling down. But to make the dam homogeneous and all one piece, they put these shear keys in the joints between the monoliths. You can see here they're quite zigzagged, and the intent is to interlock the blocks together so that the dam acts as a unit. But then you don't want to have bond between these monoliths because you have high temperature and low temperature in a dam, and it's going to contract, and you don't want to have cracks form in the dam. So these are called contraction joints. It relieves the tensile stresses in the dam that are formed by thermal stresses. And then this thing here, that's a gallery in the dam. Those are access tunnels so you can get inside the dam. They have instrumentation, or they might have drain holes, vertical drain holes that as water seeps in through the concrete, they intercept the water and take away any uplift pressures in the dam. Here's an arch dam being built. Here again, here's these 50-foot by 50-foot blocks. You can see the shear keys between the monoliths, and then they built it. It's called high block and low block, so that they're letting the temperature get out of the concrete as it hydrates, and then it doesn't show here on any of these on this photograph, but they also on the top of each 5-foot lift, they put a coil of piping along the surface, and then the next layer of concrete buries those pipes, and they run cool water through these called cooling coils, and that actually takes out the heat from the concrete, and that's an additional way to not let the dam crack as it cools. And again, there's no reinforcement in an arch dam. It's totally, all the tensions are eliminated from the shape of the dam. Here's a East Canyon Dam that I showed before, that 260-foot high thin arch dam. You can see the monolith. Look how narrow that is, and then it stays that narrow all the way down. It's only 7 foot thick at the top, and then it's only 26 feet at the base. So it's an incredibly thin dam, but it's and so what we're trying to do in the dams industry, we model these in the computer and run an earthquake through, and we look at the stress patterns that get developed, and we predict cracking and damage. But it'd be nice to compare against like a shake table test that we could actually compare it to something physical that's happened. Then the modern way to make concrete dams is called roller compacted concrete. Building an arch is pretty labor intensive, and so the industry has developed this thing called roller compacted concrete, that you build a concrete dam using like the methods they use to build a highway. So here's a truck with very dry concrete in it, and then you can place it in 1 foot high layers, and then you have a vibratory roller that goes back and forth and vibrates the concrete and makes it fluid, and so you form a solid mass of concrete. You end up with a solid, well-built dam. So the loads on the dam, here's again the weight of the dam. Pretty much that's what a gravity dam, that's how it's held in place. You have the reservoir load. When we have reservoir water coming in, you have dirt particles in the water that settle at the base of the dam. That's called silt. That adds an extra load. As water seeps under the dam, you have uplift pressures that are caused, and it's just like a boat. These uplift pressures are trying to float the dam and unweight it. So you normally put drains under the dam to capture these uplift pressures. And you have the water downstream that might be in the river. You have ice, you have barges, you have the thermal temperatures that expand and contract the dam, and then you have seismic. And seismic is a very large load that is imparted on the dam. The interesting thing about seismic is that when the earthquake hits, you have the inertia of the dam that moves back and forth, but you also have the inertia of the reservoir water that sloshes back and forth. And so that's called hydrodynamic interaction. And then those two forces are interacting together, that if we do a large shake table test, we'd have to have the reservoir water in the test also. Here's a current day finite element model of a thin arch dam, Mar Point. We did blast loading and seismic analysis on Mar Point, and you can see these individual cantilevers that were built, and you can see how thin they are. And then when you do a seismic analysis, you want the ground motions to go through the topography and impact the dam correctly. So here we model the whole topography. So here, this little dark area, here's the dam right here. This little tiny thing is that large dam. And then we model a huge extent of the foundation to get the seismic loads correctly going in. So let's just look at how concrete dams have failed in the past. Here's Gleno Dam in Italy, and it failed due to a large flood. It was built it's a multiple arch dam. So remember, it's hollowed out, and the upstream face is sloping underneath the water to add extra weight. And they started building the dam as a masonry dam. Well, masonry can't carry tension. And so the bottom part of the dam is built with masonry. And then they changed the design to a buttress dam. It's supposed to be a gravity dam. They changed it to a buttress dam, I guess, to save material. And they hollowed out the dam. And so the construction was from 1916 to 1923, and it failed in 1923 on first filling. They had a flood when they were filling the reservoir. And so remember, I talked about how the consequences can be huge for a dam failure. 356 people lost their lives downstream when this failed. Here it shows the failure. The masonry, it just failed in shear. The masonry couldn't hold the shear stresses because it didn't have the weight. If it would have been a gravity dam, it might have been fine. This whole centerpiece collapsed. Here's a Malpasset Dam in France. It failed. It's a fairly modern dam. It was built in 1959, and it failed to a foundation movement. Remember, I said that the foundations have to be really very solid rock foundations, and because it's an arch dam, and this was the thinnest dam in the world, and it failed. And everyone thought it failed because it was so thin. But they reanalyzed it. The design was good. The construction was good. The thinness of the dam didn't contribute to the failure. And what happened was there wasn't a thorough enough geotechnical investigation in the foundation, and there was jointing in the foundation that was adversely oriented. And as they filled the reservoir, uplift started seeping into those joints in the foundation and unweighting the abutment, and the large rock masses that were there started unweighting those rock masses, and they slid out and took the dam with it. So it was and This killed 421 people downstream. Here's a modern day picture of the dam. See how well the dam was built. Here's all the aggregate. Here's the interlocking cement in between, and the dam was solid. But this whole left side of the dam slid out and broke. The rest of it just went along for the ride and broke. Here's St. Francis Dam in California, and it failed due to a landslide. You can see it's a gravity dam, a curved gravity, so it's incredibly strong and stable and should be fine. There's really no reason for this dam to fail, except that back when it was built in the 1920s, they did not have professional engineering licenses that people had to obtain to be a design engineer. The man that designed this dam, Mulholland, was a self-taught civil engineer. They built the dam, and he unknowingly built it on a landslide. And so when they were filling the reservoir, the uplift pressures seeped into the foundation and made the the tip of the landslide, moist and wet, and unweighted the toe of the dam, and the whole this massive dam. Look how it's built very solid, and look at the size of these pieces. But when that landslide hit, it just took the dam for a ride, and again, it was the foundation. Here's a Viant Dam in Italy that I showed before, the extremely thin arch dam. It had a massive upstream landslide. The dam performed very well. But when this landslide occurred, 2,600 people lost their lives. And the sad thing is that if the designers knew that there was a landslide upstream, but they didn't think the reservoir would do anything to the landslide. Look what happened. So when they were filling the reservoir, the toe of the landslide was being uplifted by the moisture in the water, and this landslide, they even haven't had it monitored. It started sliding, so they lowered the reservoir, and it stopped sliding. And so the head geologist on the site said that, well, it should be no problem if we raise the reservoir a little bit and it starts sliding, we'll lower it. And if we raise it a little bit, we'll lower it. And then finally, this landslide should stabilize. Well, they went through this cycle for about a year, and one evening they rose the reservoir and the landslide started sliding, and they lowered the reservoir and the landslide did not stop sliding, and you can see that the volume of this landslide is 2.5 times the volume of the reservoir. The landslide slid into the reservoir. The water sloshed up and destroyed a town on this bank, on the opposite bank here, and then it went over the dam with a 350-foot high wave. The dam was fine. The dam withheld that unbelievably. And but here's the town below, Longarone Dam. Here it was before, and here it's after. So it can be devastating, the power of water behind a dam. So how have concrete dams performed in earthquakes? Actually, they've performed very well. And like I said, there's been no earthquakes that have failed a dam, except one concrete dam that had a 30-foot displacement and caused a lot of damage. So I'll show you that. But back in the 60s, people thought the earthquakes, just the natural frequency of a dam was such that it didn't match up with an earthquake, and that an earthquake really couldn't negatively impact a dam. But Koyna Dam in India was the first dam that was damaged with an earthquake. Here's the shape. And we later know that it's not good to put changes in geometry in dams because they attract stress. It's a stress concentration point during an earthquake. So this dam is subject to a 0.63 ground motion, and it cracked right there. Here you can see it cracked right at that kink on both the downstream and upstream sides. And then it formed, it cracked all the way along here. And so that started a lot of the earthquake engineering on dams. And people like Dr. Anil Chopra from Berkeley, Ray Clough, Penzine, all these great names in the dams industry started because of Koina Dam. And the interesting thing is that, so they put these buttresses on the downstream side of the dam to stabilize the area above the crack. But I'm not sure how well this is going to be formed seismically, because they built in a change in geometry right along the top of these buttresses. So it might, if they get another earthquake there, it might develop cracks right at the top of these buttresses. Here's Ambiessa Dam in Italy. It's a thin arch dam. And when they were building it, they did run a shake table. I don't have any data on it. I just know that they did it, and they got the model to fail at 0.95 G horizontal and 0.76 G vertical. I don't know if they just cracked it, or they damaged it, or it actually failed, or I don't know a lot of the details. But that's one of the first instance of a shake table test on for a concrete dam. And then actually, when they built the dam, it actually had an earthquake of 0.36 G, and it came out fine. No reported damage at all. So you see this a lot. A lot of concrete dams have been in earthquakes up to pretty substantial earthquakes, but they come through fine. But they've never been subjected to the maximum credible earthquake that the geology or the seismology in the area could produce. Here's Kasho Dam in Japan. It's a gravity dam, see, straight across the canyon. It had an earthquake, and they measured 2G at the crest. They had over an inch displacement on the one abutment. And this dam came through fine. No damage to the main dam. The piers were fine, and the only damage were cracks in this control building that's on the upstream side. You can imagine it's hanging off the upstream side of the dam. So I would think that would be shaken pretty well. But it just cracked, actually. Here's Tichi Dam in Taiwan, an arch dam. They measured 0.86 G at the crest right here. They had an instrument right here on this spillway in the center, and 0.86, and it has very little damage, no major cracking or cracking in the main body of the dam, and all they found were just some spalling at a parapet wall on the top of the dam, and there's just minor displacement between the two monoliths, where this vertical contraction joint divided the monoliths. But that's pretty minor damage for 0.86 G measured here at the top of the dam. Now, when I might mention that when an earthquake hits a concrete dam, you have a certain ground acceleration at the base of the dam, and the motions amplify up as you go up the dam. So depending on the height of the dam, the accelerations at the top of the dam can be 2, 3, 4 times the acceleration as it was at the base. It is at the base of the dam. Here's a Seferi Dam in Iran. It had it wasn't measured, but they estimated the peak horizontal ground acceleration to be 0.71 G. And again, this is a buttress dam. And it actually cracked. It didn't fail. This top piece didn't slide off or anything. It cracked. And so they had cracking at the top of the dam, some leakage through these cracks. And they repaired these cracks and put post-tension anchors in. And the dam's operated today. So it performed very well. Takao Dam in Japan, it's a straight gravity dam, massive dam. It was subjected to an earthquake of 0.4 G, and then just 6 days later, another earthquake that was 0.38 G, and to show you how much amplification. So at the base of the dam, the peak horizontal accelerations were about 0.38, but at the crest of the dam, look how they magnify. The accelerations magnify at the top of the dam. And so they measured 2G at the top of the dam. And so what happened here? Here you can see this tower over here, this elevator tower and a building. And basically, same thing here too. This building was damaged. You can see the cracking that happened in the building. And there's small offsets in the parapet wall, but basically no damage to the main part of the dam. And even at 2G, this building came through fairly well. Normally these buildings are reinforced. The dam itself is not reinforced, but normally these buildings or these parapet walls are reinforced. And then Shikang Dam in Taiwan. Now this dam was damaged during an earthquake. This dam was completed in 1977. The earthquake happened in 1999, and it had 0.51 G at the site and 0.53 vertical G. So it's kind of a spillway dam. It's a gravity dam that has all these huge spillway gates on top. None of these piers failed downstream, but the left side of the dam was uplifted 36 feet. And so this is what happened. So if you have a fault that's going through the gravity dam, you can have tremendous damage. But the interesting thing is, a lot of these piers were cracked. They had to be replaced. But the interesting thing is they didn't fall downstream. It didn't release the reservoir simultaneously, and everything went downstream. So these kind of collapsed and fell on one another. So the reservoir was the flow out of the spillway gates was much less than when they opened the gates. So there was no flooding, and the dam actually performed away from this area pretty well. And in this area, it didn't collapse through. So you can see here, here's the original height of the dam. Here's the on the other side of the fault, and look at the damage that occurred. So yes, if you have a fault and offset in a dam, there can be tremendous damage. But this is the only case where a concrete dam has been damaged this severely. So why do we need large-scale testing? Well, because in the dams industry, just like any other industry, civil engineering, we're predicting probabilities of failure for different loading conditions, and this helps prioritize work being done on different projects, and what's the risk to downstream populations, and are the dams safe? And because the downstream consequences can be so enormous, we want to get a good handle on just the response of a concrete dam to an earthquake. We think we have a pretty good feel because we've done all sorts of finite element analysis, seismic analysis of all the concrete dams. But it would be nice to validate the studies with against actual tests. So the one thing that's difficult is the small scale testing. It's hard to get the similitude of all the different pieces of the test correct. you have the concrete density, the modulus, the compression, the tensile strength of the concrete. You have the foundation rock and its properties. You have the dam to foundation interaction. It's good to have if you're going to look at the failure of a concrete dam, you want to get the failure and the cracking of the concrete correct. There have been small scale shake table tests done, but they never use actual concrete for the material in the dam, the model dam. The Chinese did some shake table tests with rubber dams, or they used some kind of plaster filled with lead and trying to get the similitude right, but it just wasn't concrete. It didn't fail like concrete. So that'd be nice to get that. With a larger model, those similitude issues are a lot less. Then you have the water and the hydrodynamic interaction of the water. Then you have the non-linearities, the vertical contraction joints, crack propagation, sliding, or a kinematic movement of blocks once they crack. So at the Bureau of Reclamation, we have a shake table. It's not near as big, as the LH Post, but and it's just a single degree of freedom, just with a sine wave. So I'll show some videos. We had a 3-foot high arch dams that we put in the shake table, and that actually gave us a feel for how an arch dam, might fail. And then the Corps of Engineers did some small scale tests. There were a 9-foot high 2D gravity dams of Koina Dam, the first dam that in India that cracked. But the same thing, their shake table is a one direction sine wave. We did do an outdoor blast test of a 3D arch dam model down in Fort Polk, Louisiana. Homeland Security wanted to know what blasting could do to a concrete dam. So we did a 15-foot high arch dam models and had explosives in the reservoir. And then then FEMA is interesting. In 2008, Reclamation, we were going to be partners with FEMA and Homeland Security to do a large scale test in San Diego on your shake table. We had, they were going to grant us $3 million to do a large scale test, or it was maybe 15, 20 feet high, 30 feet high, and on the shake table. And the week that we were going to announce that we got the funding, the financial crisis hit in the United States, and we lost all the funding. All the funding was pulled from FEMA, and we never really got it back to do it. So that's too bad. So just static tests, large scale tests of when they were building Hoover to compare model testing to analysis. Here's a large scale test in the reclamation lab in Denver of all these strain gauges, and they would load a section of Hoover and see if their analysis matched the stresses. Here's a large scale test of an arch. They would crack it. They were worried that if they built an arch dam, would it crack through, and would it how would it perform against a rock abutment? And you can see the size here. Here's some bookcases against the wall if you look through the arch. But they did that. And so here's some of the small shake table tests. Here's a little arch dam, and we had the vertical contraction joints. So I'll just show this. And you can see how what we learned, one thing was that it takes a long duration for a arch dam to fail. See how it goes and goes and goes. And so I'll rerun this. It starts getting out of shape, and you start losing arching action. And then once it loses arching action, these cantilevers can't stand there by themselves in gravity action, and the whole thing just collapses through. Here's another view of a different model, but the arches always seem to crack, have a real low crack down near the base, and then see how that arch just got out of shape and eventually fell through. And then we did a test of a thin arch dam. So I guess civil engineers get excited with small scale testing. I'll run it again.
Hey, Larry, I just wanted to draw attention to the time. We have about 7 minutes left, and I didn't know.
Okay, perfect. This is my last slide.
Okay.
Perfect. So that's it.
Thank you. We only had one question kind of be asked in the Q&A session, but we can open it up to others to unmute. The question, I don't know, Andres, if you want to ask it again or want me to read it. So he asked about the 3D finite element model with the topography. What criteria did you use to define the extent of the soil domain?
Oh yeah, so we do different sensitivity studies for that. You know, when you deconvolve the motions, that's the other thing. You have to pick the control point, whether it's at the top of the canyon or the middle of the dam or at the base. And so and then the topography, what we like to do is start with a large topography and then slowly get smaller, and then once the motions change a lot, then we stop right there. So we start with a large foundation and get smaller to the point where we can run something smaller.
And what kind of boundary conditions were needed at the ends of the domain? Or
oh yeah, so we use so that model was with LS Dyna from Livermore, and we use perfectly matched layers.
okay. So I had another question from Andre Philippe. His question was, how many of the concrete dams that you mentioned, example from the Bureau, are instrumented with sensors for seismic monitoring?
Oh, quite a few. So we have 380 dams, 90 of which are concrete dams. And we used to have all the dams were monitored for seismic, but then that got to be pretty expensive. So we looked at the probability of getting motions at the different dams, and then picked the ones that had the highest probability of occurring, and those are the ones that we kept the sensors at, the strong motion sensors. And then we normally we'll put a sensor at the base of the dam. We try and put it like at mid height, and then across the top of the dam, and then out at a control point out away from the dam on a rock outcrop.
Okay. As a follow-up to that, considering the increasing concerns regarding seismic safety, do you think it would be beneficial to invest in the installation of permanent monitoring systems?
Yeah, at certain sites, yes, I think so. And most of them do. You know, those dams that we kept the stations at, they're going all the time. So we monitor at all the dams. We do static. We measure displacements, uplift pressures, different things like that. But it's the strong motion instruments that we kind of limit the number out there.
Great. I have two more questions. One from Enrique Simbort. Did you calibrate the model of the Morro Point Dam using measured data from vibration tests?
We did. That's a great question. So we're doing that more and more, and that's definitely the way to go. Professor Z. Duran, when he was getting his PhD, that was his PhD project, was to do vibration testing of Morro Point. And so we used his data from his PhD to calibrate our model when we did more point. And so that's becoming standard practice, just to do vibration testing and ambient testing at the sites, get the natural frequency, and then we can use that to calibrate. So excellent question.
Great. And so another one I have, and then I think Joel has his hand raised, so he can jump in a second. But how important is interface sliding as a mode of potential failure for typical seismic evaluations of concrete dams? And is this commonly sensitive failure mode?
Yes, great question. It definitely is. So that's, so gravity dam is held there by its weight. And so one of the key failure modes is sliding, either in the foundation along a joint, or between the dam and foundation contact, or within those lift lines. You place the dam in 5-foot high lift, so you have all these joints, and most of the time they're bonded together, but sometimes they're not. And so all those are slide planes that we have to look at. And so we normally model those with contact surfaces, and then we'll put the earthquake in and see how much it slides. But that's another area is to calibrate the contact surfaces and make sure we're getting good results from those.
So somewhat indirectly related is one more question. You mentioned how it is difficult to precisely model real-world constraints on a small scale. With that in mind, how accurate have the shake table tests that have been in predicting failure modes observed in dams historically?
Oh, so the small 3-foot high models the shake table models that we did at Reclamation, we then we were using Abacus at the time, and we did an explicit analysis of those models, and we could pretty much match the failure mode, but we couldn't match the timing. It seemed like it was very difficult to get the analysis to fail at about the same time as the model did. So the timing was difficult, but the actual failure mode we're getting fairly close. So that was encouraging.
Okay, and Joel, you have your hand raised.
Yes, Larry, thank you very, very much. I have two questions. One is, you talked about the drain that is, below, I would say, the heel of the dam. To lower the uplift pressure. I imagine it's very important to lower this uplift pressure early on, from when you go from the heel of the dam to the toe. And how important is it to maintain these drains so that they don't clog up? Because if they clog up, I imagine that you could have a huge buildup of the uplift pressure and lose a lot of safety. So what is done, in real dam to maintain these drains?
Yeah, good question. So the drains are at least 2-inch diameter, preferably 3, and they're spaced every 10 feet across the canyon. And then they go down at least 40% of the height of the dam, so way into the foundation. And then the water is intercepted by that, and then comes out. And then typically you put piezometers in the foundation and monitor the uplift pressures. So if you see those pressures degrading, then you have to go back and clean those drains. So they clean those out with high pressure water, or if it's too calcified, they have to go in with drills and re-drill those drains.
And then the water coming out of this drain, it comes out laterally, or it just follow the base of the concrete dam and go downstream directly?
Yeah, good question. So on that one picture, I showed the gallery, that tunnel in the dam. So those are inspection galleries, and they're also drainage galleries. So the drains come up into those galleries, and then there's little troughs that the water flows out, and then they flow downstream. They have an outlet where they can flow downstream. Sometimes they have sump pumps where they'll pump the water out and they'll pump it out.
I see. And my second question is, you showed the Ambiesta Dam in Italy, and you mentioned a shake table test. Do you know which shake table was used to do this?
I do not. I don't have any information on it, so I apologize.
Sure. No, that's it, Lely.
Okay, super. Well, that was excellent, Larry. Thank you so much. I think we are at the top of the hour, so we probably need to end it, but this has been recorded. So for people that had to leave early or whatever, we will post it on our website. And we really appreciate your time, Larry. It was very interesting.
Well, thank you so much, and thanks for asking me. I appreciate it.
Thank
Yeah,
you all
thank
for
you.
attending.
Thank you very much. I will just add one thing. Thank you very much, Larry. Those of you who would like to be on the mailing list of NERI, send us an email and then we will communicate this to the coordinating office of NERI. And if you go to our own website, neri.ucsd.edu, you can keep track of, we will make announcement of the upcoming webinars. I put it on the chat, neri.ucsd right here. Yeah.
Yep. No, you
So
sent it.
thank you very much for your attendance. Have a good evening, a good afternoon.
Thank you all. Take care. Bye.
Bye, Larry.
Bye.
Thank you very much.
Bye.